In this video, we will see how to store the valid tuples inside the data structure that we will call reversible bitset. Okay, it's a reversible bitset. It's a way to encode a bitset data structure, so standard bitset of a data structure, but it needs to be reversible and it needs to perform the operations of the logical AND for the intersection and the logical OR for the unions of the bitsets very efficiently. And so we will encapsulate, the reversible bitset will encapsulate an array of state longs, okay? So instead of just storing it into longs, 64 bits, we will use state longs so that if you update long values, if you flip one bit to the next on backtrack, it will be restored as in the state of the previous one in the ancestor node. So valid tuples is stored as a reversible bitset data structure, and internally we have an array of state long that is represented here. Okay, so this is really a state long here that is composed of 1, 2, 3, 4 long. So again, remember this normally is 64 bits, but for the sake of representation here, because we have a limited space, we just it with 4 entries, but normally it should be 64 bits. Okay, and this would be one long value in Java, or a state long. Okay, so we have got 1 state long, 2 state long, 3 state long, and 4 state long here. So just assume that it is a 64-bit long value here. So for the incremental update, we will perform a lot of this kind of operations. So if you remember the mask, which was a temporary bit set, we were doing the AND operation between the valid tuples and the mask. Question here, for instance, if you consider this as the current value for the mask, and this is the current valid tuples, as you can see, there is no need to really compute the AND on every word, because some of them, such as this one, is already 0 everywhere. So if you perform an AND between a long that is already 0, you know you will get a 0 as a result. So the idea is, instead of doing it on all the different words, on all the different long internally, we will only do it on non-zero words, and this will be more efficient. We assume that as we will go down in the search tree, the valid tuples will shrink, and we will get more and more situation like this one, in which a complete word is composed of all the bits 0. So to perform the operation only on non-zero words, we will add here an index array, and this will be exactly the same idea as for the main representation. We will have a prefix of all the indices of the words that are non-zero, and the one at the end are considered as 0 words. So in this case, we see that we have 4 words, and only 3 of them are non-zero. And this is why we have a size of 3, and the non-zero words are the one at index 0, 1, and 3, which is the prefix here in my index array. Okay, this is the mask, and so if you perform an operation with this mask, we will only do it on the non-zero words. And these are all the operations that can now happen on non-zero words. You can add to mask, okay, and so you will only change the corresponding words in the mask corresponding to the non-zero words of my valid tuples. If you reverse the mask, again, you will only flip the words that are non-zero. So you will do it for this one, and this one, but you will not flip this one. This is useless because you know that 0. If you want to intersect the mask, again, you will do it only on non-zero words. And if you, so this is what you will do here. So you do only all the operation for non-zero words, and this is why you can gain a little bit of efficiency. This is an optimization that you can do to have more efficient bitwise operations. So let's consider, for instance, the operation of valid tuples, and you intersect with the mask. So you will go in that direction, and you will do the logical AND operation, because it's an intersection between all the words. So you take the word 3, you do the logical intersection, and you will update it here. So if you take the intersection, you see that they are exactly the same. So you will get a 1 here again. and so the word is non-zero. Then the next word that you consider is the word number 1, and you make the economy, okay? You will spare the computation on this word because you know that it's 0. So you immediately jump to the word number 1, you do the logical AND, and here, as the result, if you do the logical AND, you see that you will end up with a 0 word because there are no bit in common here, and so you've got a 0 word, and what it means is that since this word is 0, you can flip it with the 1 at the end. Okay, so you will flip it with the previous one. Okay. And you can decrease the size. Okay, so if I change again, so you are doing this one, you do the logical AND, and you will flip it with the previous one, which means that you will flip it with this one, and you will decrease this one by 1. Okay, so you change the 3 and the 1 of the indices just to reflect that the word is now 0. Okay, so now it's 0, you flip it, and you decrease the size by 1. And the intersection for the last one, the one at index 0, in this case, is unchanged, so we keep it as it is. So the API of the reversible sparse bitset is this one. You can add to mask, and you can do intersect mask. And so if you want to update on the domain of X, so this is the from scratch operation, you need to do valid tuples and support X3, support X4, if you remember the previous example. So the way you would perform this operation using the reversible sparse bitset is first to add to the mask the support of X1, then you add to the mask the support of X2. So what you get is, oh, sorry, there is a typo here. So you add to the mask the support of X3 and you add to the mask the support of X4, like this. And then you do the intersect mask. Okay, and so this is the way you update the valid tuples. If you want to update based on delta X, this is a little bit different. You add the support of X1, you add the support of X2 to the mask, then you reverse the mask. And reversing the mask means you take the complement, the bitwise complement, and then only you do the intersect mask. So this is very efficient, and on backtrack, once you will backtrack, you just restore the size, okay, as it was here, and the state long, of course, will also be reversed, and so you will recover all the words that are non-zero. So if you do that, you will recover the word number 3 in this case, and that is back in the set. So you backtrack, and you recover it as it was before, okay, in the set, and you recover words that are non-zero now.